We're going to continue talking about correlation and regression by talking about regression. So when we talked about correlation, you might have been saying, great, so we know if the line fits or not, but how do we find the line? You're in luck. Regression is going to tell us about how to find that line. So, given a collection of paired sample data, the regression line, or line of best fit, because surprise, surprise, it has the best fit for the data, or the least squares line, you'll see why it's called that sometimes in a little bit later, that's the straight line that best fits the scatter plot of the data. So, since it's a line, we have a linear equation, and we say y hat equals b sub 0 plus b sub 1 times x. It's the equation of a line, slope-intercept form. B sub 0 is going to be our y-intercept, b sub 1 will be our slope, x is going to be our independent variable, also sometimes called the explanatory variable or predictor variable, because we're going to be using it as input to predict our y value. Y hat, because it's a predicted value instead of the actual value for a data point will just be y. The predicted one will have a y hat, have that little fancy hat thing on top. And that's our response variable or dependent variable or a predicted value. So our goal is to find the equation of a regression line. So a little notation before we get started. When we're using these equations of lines, again, B0 is our y-intercept, B1 is our slope, and our equation is there. When we're talking samples, we're going to use our typical English alphabet letters, and when we're talking populations, we'll use their Greek equivalent. In this case, B's become betas. So, we need to check some requirements before we get going for finding a regression line. And you'll notice that they are, in fact, the same requirements that we checked when we were looking for correlation. So our sample of paired data needs to be a random sample of quantitative data. If we look at a scatter plot, it needs to look like it's approximately a straight line. And our outliers, we need to not have them. So we need to take them out. And sometimes it's good to show the effects that they have by calculating what a regression line would be with and without them. Now, note that, again, requirements 2 and 3 are simplified attempts at checking some formal requirements. Those formal requirements are listed here. We're not going to worry about them. The simplified attempts are going to be good enough for us. So, if we want to find the equation of a regression line, we need to find the slope and the y-intercept. So, to calculate the slope, we use b sub 1 is going to equal our correlation coefficient r times the standard deviation of y divided by the standard deviation of x. And when we want to find our y-intercept, we're going to use the slope that we calculated, and we'll use the mean of the values of x and the mean of the values of y to find our y-intercept value. Now, these give you a really good idea of what's going on. And if we calculate our R value to start with, if we're looking for our correlation coefficient as well as the regression equation, this is the way to go. So I don't entirely agree that this is easier to do when you're doing manual calculations. If you have to find R already, if you have to find that correlation coefficient, which it's a good idea to find out if you should really be using your regression line or not, then you might as well put in the work for this type of stuff when you're calculating R, and then use the work that you did previously for finding b sub 0 and b sub 1. Now, if you haven't done that work and you don't have to do that work, then this is your better way to go, because then you can just bypass the having to find R thing. This also is the way computers work. This is the way to program it into a computer a little bit more streamlined. So we have formulas for B1 and B0. And again, if you're using these, just like we did when we were talking about correlation, finding the R value, highly recommend you build up a table and find x squared, find y squared, find xy, and find the sums of all of your columns so that you can kind of plug and chug here, all right? So we are going to always round B1 and B0 to 3 significant digits. Right? So we need some kind of universal rule. That's what we're going to use. This will work almost always. So technology is a super common thing to use here. Again, we're going to be doing things by hand, but we want to know how to and be able to read the output of technology to help us out. So we're going back to our chocolate consumption and Nobel laureate data. So here's our data set that we had. And checking our requirements, it's simple random sample. We'll say yes. Last time we had a little bit of hesitation about that. We'll say yes this time just for the sake of this example. And looking at the scatter plot, again, pretty much a line, and there's no outliers that we really see. A couple of further away, but again, not outlier type stuff. All right, so technology. We can use tons of different things to find an estimate here, but they're all going to give us a regression equation that can be expressed as y hat equals negative 3.37 plus 2.49x. So y hat is our predicted Nobel laureate rate, and x is the amount of chocolate consumption. So this is what the output looks like for 7 different programs. And you'll notice on all of them, they tell you either the equation spelled out for you, or they'll tell you what parts are what for the equation. So take a look at those, make sure that you can see and find all of the parts and know where to look for them. All right. So now we should know that the regression equation is an estimate of the true regression equation for the population of paired data. This estimate is based on one particular set of sample data, but another sample drawn from the same population would probably lead to a different equation. Hopefully that's clear to you, because our equation clearly was taking into account all of our x and y values in our sample. So if we change some of those, the output's also likely to change. All right, so now let's get out of technology, and we're going to use that first formula. Since we know the R value already, we already found the correlation coefficient for this. We're going to use that to find B1 and B2. So we already checked our requirements, so now we're going to start off by finding B1. We use our formula of R times the standard deviation of y divided by the standard deviation of x. And when we multiply all of that out, we get 2.493135. So now that we've found our slope, we can find our y-intercept. So our y-intercept, b sub 0, equals our mean of our y's minus our slope times the mean of our x values. So plugging all of those things in, doing our arithmetic, we get negative 3.366675. So now we have our slope is 2.49 when we round it, and our y-intercept is negative 3.37 when we round that. And so we have our regression equation as negative 3.37 plus 2.49x. So again, y hat is the predicted Nobel laureate rate, and x is the amount of chocolate consumption. Always a good idea to define your variables every time you are writing anything like this out. So we want to also take a look at graphing our regression line and make sure it actually looks like it fits with our data. So take a look at our data in a scatter plot, and we graph our line, and it looks pretty good. So we're all right. So let's talk about whether we should be using this thing to make predictions or not. So really the whole point in finding a regression equation is to be able to make predictions. So let's talk about whether we should or not and when we should or not. So we need to consider whether our model is good or bad. So you take a look at your scatter plot, you take a look at your regression equation on it, and you say, hey, that looks pretty good. You probably have a good model. If it doesn't, then it's a bad model. Also, if the context of the problem just doesn't make sense to be making predictions with this thing, don't. All right? This is really a common check or common sense check here. All right. So if it looks bad, feels bad, don't use it. If it seems all right, use it. All right. Develop that gut feeling. So the other two things that you need to look at, the first one's correlation. So looking at your linear correlation coefficient R, if it indicates that there's a linear correlation between the two variables, then you're probably in okay territory. Also, the scope matters. So when we want to make estimates, want to make predictions, we don't want to go too far beyond the scope of the data that was used to make the line. So what I mean by that is if your data stops in 1990, maybe don't make predictions about 2025. All right. So what we need to do is we need to be kind of close to the scope of our X values that went into finding our line to begin with when we're making predictions. So when we're completely within that, it's called interpolating. And when we go outside of that, it's called extrapolating. And we need to be really careful that we don't extrapolate very far at all from within the scope of our sample data to begin with. So again, here we are, all right. If we want to predict a y value and you look at your regression equation and it's not a good model, so for whatever reason, you look at the graph, it doesn't look good, or you see that the R value indicates that there's maybe not a linear correlation, or if the prediction is way beyond the scope, then you're in the no category here. All right. So if that's the case, then what we do is we give the mean of the y values as the prediction, right? Regardless of what our x value is. If, however, the regression line looks pretty good on your graph, the R value says, hey, there's a linear correlation there, and like the prediction is pretty much in the scope of the available data, then you're in this yes category. All right? And if all three of those things are true, you're in the yes category, you can use your regression equation to make a prediction of a y value. So here's two examples. We're going to use the chocolate/Nobel data to predict the Nobel rate for a country with chocolate consumption of 10 kilograms per capita. So let's talk about that. Well, it's a good model. We have seen that the correlation coefficient says yes. We looked at the picture of it. It looked pretty good. The graph looked good. And 10 is within our data. So the scope of our data. So this is a pretty okay thing to do. So we substitute 10 in for x into our regression equation, and we get a prediction of a rate of 21.5 Nobel laureates per 10 million people when there are 10 kilograms of chocolate consumed per capita. Right. Now, on the other hand, predicting the IQ score of an adult who is exactly 175 centimeters tall, height and IQ, not related. All right, we don't even have to take a look at this to know that. So our best prediction is going to be the mean of IQ scores, regardless of what the height we put in is. And the mean of IQ scores is 100. So we'll make the estimate or the prediction that the IQ of a person with exactly a height of exactly 175 centimeters is going to be 100. So again, in summary, part A, paired data had a good regression model, so we used that to make the estimate or prediction. And part B, no correlation, so we instead used the mean as our estimate. Right? So let's talk about another key concept called marginal change. So in working with two variables related by a regression equation, the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. So the slope in the regression equation represents the marginal change in y that occurs when x changes by 1 unit. So let's look at an example of that. So we had our 23 pairs of chocolate Nobel data. Those 23 pairs gave us a regression equation of y hat equals negative 3.37 plus 2.49x. So the slope was 2.49, And that tells us that if we increase X, or chocolate consumption, by 1 kilogram per capita, the predicted Nobel laureate rate will increase by 2.49 per 100 or per 10 million people. All right. So for every additional 1 kilogram of chocolate consumption per capita, we expect the Nobel laureate rate to increase 2.49 per 10 million people. That's what we're looking for. When you're asked for the marginal change, that's what you're looking for. What difference does a change of 1 in X make to the value of Y? Now, we've been throwing around the term outliers in what we're checking, but we haven't actually defined it. So in a scatter plot, an outlier is a point that's lying far away from the other data points. And those outliers, they fall into the category of what we consider an influential point. So paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line. So let's take a look at this. So on the left, you'll see our graph that we looked at before of chocolate consumption versus our Nobel rate. Now, if we add a point that's an outlier, or an influential point, at 50, X is 50, Y is 0, and we go through and we calculate what our regression line should be, again, we get what we see on the right here. Now, looking at that, that line is dramatically different because all of our original data is on the left of that graph. And so we really should have a fairly steep line given this data if we were going to be fitting our data the same way we were before. So that line has changed even more dramatically than it looks like it has. So by all means, be careful about influential points and outliers. All right, let's take a look at residuals. So the residual for a pair of sample X and Y values, the residual is the difference between the observed sample value of Y and the predicted value of Y using the regression equation. So to find the residual, we take the observed Y value and subtract the predicted value from it. So what that looks like on a graph is basically the distance between the point itself and our predicted value. You'll notice that if the actual value is above our regression line, then our residual is positive, and if it's below, the residual is negative. Now, the reason that all of those things are showing as squares with side length of the residual is because we want something called the least squares property to be true about our regression line. So the least squares property, what that is, a straight line satisfying the least squares property is it does that if the sum of the squares of the residuals is the smallest sum possible. So if we're looking at the areas of all of these squares that we're making when we look at the residuals, we want basically the combined area of them to be as small as possible. And if we have done that, then our regression line is the best one that we can have, right? That right there, that property about our regression line, is why it's called a least squares line sometimes. So to check that we're doing good with our residual, we can look at a residual plot. And this can actually tell us if our regression line is good or not, or even if a linear correlation is a good idea or not. So a residual plot is a scatter plot of the X and Y values after each of the Y coordinate values has been replaced by the residual value, Y minus Y hat. So we've got a residual plot is a graph of the points X and Y minus Y hat. So to construct that, we need to find all of our residuals, make all of those points, and we'll draw a horizontal reference line through the residual value of 0 so that we can easily identify what residuals are positive and which ones are negative. So let's look at analyzing our residual plot. We want a residual plot to not have any obvious pattern, and we also don't want a situation where, like, as we go left to right, it's getting like bigger or getting like smaller. So we'll look at what that looks like in a picture beyond me waving my hands in just a second. So again, looking at our chocolate Nobel data, we can go through and find our residuals. So here's an example of finding one of them. So taking our actual y value of 5.5 and the prediction of 7.84, we find a residual for that of negative 2.34. And that was at the x value of 4.5. And we do that for all of our points. You can see that one showing up here at 4.5. We have a value at negative 2.34, and we've plotted everything else as well. So in a residual plot for a decent regression line, what we want is it to look kind of like this, where there's no real pattern happening. You might be able to convince yourself there are patterns, but you have to do some convincing. And that it's kind of staying about the same distance from that residual line also. So some examples of good and bad things. So the one on the left, the residual plot, there's no real pattern. It's not getting wider or narrower, so it looks pretty good. The one in the middle has kind of like an ocean wave or a mountaintop type of thing happening where you can kind of see a pattern happening. You could play connect the dots and really draw a line with it and not have to be like bouncing around to do it. Whenever we see some kind of obvious pattern like that, that suggests that the regression equation is not necessarily a good model. And a lot of times what it's suggesting is that a linear model is just not going to be a good model. Similarly, if we see it becoming wider, like we have here on the right, it starts really narrow, really close to that residual line, and it starts ballooning out. Again, this is a sign that that regression equation, it's not a good model. In fact, linear models, maybe not a great idea. And similarly, if that same pattern happened in reverse, again, linear model may not be great. Regression equation that you have, definitely not good. All right, so that's all there is to this regression stuff.